So here's an example of total magnetic field produced by different wires and then added together. We have to worry about the fact that magnetic field is a vector. We have to produce the magnetic field vector for each of the two wires, add them together. The two wires are both parallel to the z-axis. This is y-axis, vertical axis here, and x-axis horizontal. So the z-axis is coming out toward us. This top wire is parallel to the z-axis. It's also coming out, the current is coming out toward us. The bottom wire is parallel to the z-axis. The current is going in away from us. Each of these currents produces a magnetic field at point P. We want the total magnetic field, so we want to find out what each of them is, sum them, find out the total magnetic field at point P. Since we know that's a distance x away from the origin, we just call that distance x, and we'll have P for any x, and we'll be able to plug in any x that we want. Right-hand rule for the top wire shows you that, well, you know the magnetic field circles around the top wire. The right-hand rule shows you it circles counterclockwise if the current is coming toward you. And so at this point P, that counterclockwise circle, the tangent to that is a magnetic field in this direction, up and to the right. The lower wire has a current in the other direction. The magnetic field circles around clockwise. And so the magnetic field at point P is down and to the right. Because this straight wire has a very high symmetry, you can use Ampere's law to find the magnitude of this red vector B. So I've drawn the more of the circle. The red vector B is constant in magnitude around this circle. I've just drawn a couple of them. Here's one here. Here's the one at P. Constant in magnitude because the radius around this wire is constant and because the wire has a very high symmetry. So at this distance away from the wire, every magnetic field has this magnitude. It's only the direction that's changing. To find the magnitude, we use Ampere's law. Now Ampere's law has magnetic field dotted into dl, where dl is a distance along this path, this circular path. So dl is a differential distance along this path, and that means it's tangent to the path. Because it's tangent to the path, it's parallel to the b-axis, because the b-axis is also tangent to the path. So the dot product of b dot dl is just b times dl. B is a constant. That's the magnitude of b, because we're out at the same distance from the wire everywhere along this circle. Circle's centered at the wire. So the left side of the Ampere's law has the integral, line integral around a loop. B comes out of the integral because it's a constant. The integral around a loop of dl is just the total length of this path, and that's the circumference of that circle. It's 2 pi times the radius. The radius is the distance from this point out to point P, from the wire out to point P. This is the left-hand side of Ampere's law. It has to equal the right-hand side, mu 0, y enclosed. So when you equate those two and solve for b, you find that b is mu 0 I over 2 pi r. So now we know that b is mu 0 I over 2 pi r in this direction for the upper wire, in this direction for the lower wire, same magnitude because same current, just a different direction. When I add these two together, the y component of this red magnetic field is going to cancel the y component of this blue magnetic field, and the x component of the red is this little green one here. The x component of the blue is just going to add to that, so these two green arrows represent the two x components. They will add together to give you a bigger vector to the right. The vector will point in the x direction. The total magnetic field at point P is going to be mu 0 I over 2 pi r, the magnitude of this one, times the cosine of that angle to give you the x component, plus the magnitude of the other one times the cosine of the angle to give you the x component there. They're the same angle, they're the same amount, and so it's really just twice this. If you just look at the geometry of the situation, this angle theta right here that you take the cosine of to get that is the same as this angle theta right here. and that the cosine of that angle theta is the adjacent side A divided by the hypotenuse, which happens to be r. You can write the hypotenuse as the square root of x squared plus a squared. So we know what r is in terms of x. We know what cosine theta is in terms of x. We can plug these in and get the final b of x. The magnetic field points to the right. It points to the right anywhere along the x-axis, and this function has an x in it, so we'll see how the magnetic field varies with x.